Well, as I mentioned, folks, there's a lot in chapter 7. So the last couple of pages here, I just want to do a quick review. So the first item we talked about in this chapter is enthalpy, started with an H. And really we can think of this as heat. It's heat that's exchanged under constant pressure, which is the conditions we see in the lab. The other thing is we have this, plus or minus heat, plus or minus enthalpy, exothermic, endothermic. So if I think of a system as being like some kind of container that has a reaction going on, and the surroundings, of course, is everything that surrounds it, and I can think of heat going out to the surroundings, or the reaction, the system drawing heat from the surroundings. Surroundings get warmer, surroundings get cooler. Well, this is negative delta H. That's exothermic. This is a positive delta H, endothermic. Okay. And then one of the first ways we looked at this was said, well, what if I look at a reaction here and I think of it in terms of the energy required to break bonds, break those bonds, and the energy that I get back when I form those bonds. Endothermic, put energy in to break the bonds. Exothermic, energy comes back out when they sort of snap together. So we said, let's do it like this. Well, we said, so actually what I'm going to do is I'm going to give you the answer, and then you give it a try. The answer for this is minus 506 kilojoules per mole, and that's delta H for the reaction. So try that. If you don't get that answer, text me, email me, I'll help you with it, but try to get that answer. The other way we sometimes got this was not by actually looking at the bonds that are broken or formed, but we used kind of a recipe where I had a balanced chemical equation, and now we have this enthalpy term right there. So it says how much heat is produced when 10 grams of hydrogen reacts with excess oxygen. So 10 grams of H2, and I would like to get to kilojoules. And again, I'd like you to do that, but no, we're going to start with that. There's our recipe. I'm trying to get to kilojoules. I'm going to give you the answer, minus 1200 kilojoules. Or since it says produced, I'm not going to worry about the sign. The heat exchanged was negative 1200 kilojoules, or produced 1200 kilojoules. So see if you can work that out. If you can't work that out, then text me, email me. Then we said, okay, there's another consideration, and that is this entropy stuff, which is a lot of different definitions, but one way to think about it is, well, we know the term is entropy, but it's disorder is one way to think about it. It's disorder. It's diffuseness. It's sort of how much an energy is sort of spread out. Diffuseness. It's not a word. I just made it up. And so what we know is nature likes to do things that is exothermic. The net effect is the energy is going downhill. And nature likes to do things that increase entropy. Well, that gets complicated, but we can at least look at chemical and physical processes that seem to increase disorder. They seem to increase this sort of spread outness of matter and energy. So we say, well, melting is usually something that spreads something out, increases disorder. Boiling or vaporizing, vaporizing, evaporating. A liquid is compact and it spreads out into a gas. The last one is dissolving a solid in a liquid. Nature likes to do that too, because you've got this nice orderly solid, and boom, it spreads out into ions or molecules and spreads out into the liquid. And then we said, well, there's this way to consider all of this stuff. This Gibbs guy came up with a pretty cool relationship that said, you know what, if you calculate that takes into consideration the enthalpy of the reaction and the entropy. And actually it's looking at all of the entropy. It's kind of hidden in the math there. So delta G was Gibbs free energy, which is delta G is right there. It predicts, well, it allows us to predict again whether it's spontaneous. Positive delta G is endergonic. And the term we say is non-spontaneous. It just means that reaction, that change, won't happen on its own. You could pair it with some other reaction to give it enough energy to make it happen, but on its own, you put the stuff in some kind of container, nothing will happen. Endergonic, non-spontaneous. The other one is exergonic. And we say it's spontaneous. That means if you put the reactants or whatever change, physical change, chemical change you want to have occur, if you get a negative delta G, you get it started and it just keeps going on its own. You don't need to do anything else to make it happen. And here was our simple relationship. The delta G is the change in enthalpy minus temperature times the change in entropy. And we often can have, this is really a recipe too, we don't calculate this in Chem 51, but we can be given that value, and we can be given this value as well. So if I were to calculate my delta G, there's my delta H, and I'm going to do something funny here. Delta G equals, it's a positive 40,700 joules per mole. Now, I did it that way because notice this is in kilojoules, this is in joules. Very commonly done that way. So I always just say, okay, why don't I just write them all in joules? So 40,700 joules minus the temperature, and I can't use degrees C. I have to use kelvins. So I'm going to do that plus 273. Now I'm in kelvins. My delta S is a positive 109 joules per mole Kelvin. And let's see, when I did this math, I ended up with minus 1050 joules per mole was my delta G. So I could say, yeah, that's spontaneous. You put that stuff together at that temperature and it will happen. Now, this was hinted at a couple of times. Maybe I didn't say it explicitly. Whenever I reverse a reaction, melting versus freezing, or a reaction going one way and the reverse reaction, anytime I do that, all the signs of enthalpy, entropy, and Gibbs free energy, the sign changes. So here I have this reaction, liquid water going to gas, basically evaporating or boiling. At this temperature, 110 degrees C, it's negative 1,050 joules per mole. If somebody said, okay, I want the gaseous steam to turn into a liquid at that temperature, it's the exact same number, but it becomes positive. And it's the same for enthalpy, entropy, or delta G. Run it the other direction, the signs are opposite. All right, let's look at the very last page here, Chapter 7 review. Okay. Then we took a little side detour and we talked about how fast reactions happen. And we said, well, the reactant particles have to collide. If they're just bouncing around, not interacting with each other, there's no reaction. In fact, we call this the collision theory. And they can't just collide. They have to collide with enough energy. They have to collide with enough energy to get bonds breaking, a new bonds forming. They have to overcome the electron-electron repulsion. So they can't just gently bump into each other. They've got to hit with enough energy to get the reaction started. The other thing is, oftentimes the molecules are very complicated and large, and I've got to have the right part of one molecule lined up with another part on the other reactant molecule. It can't just be sort of a random. The alignment has to be proper to make the reaction happen. So I'll say with proper, I guess I'll say proper, with proper orientation or alignment, orientation, alignment. So that's our system. Particles have to collide. They've got to collide with enough energy, and the collisions have to be the right orientation, the right angle, the right alignment to make a reaction happen. Well, knowing that, we can talk about like, well, how can you increase or decrease the rate of a reaction? Well, the first thing I can do is increase the reactant concentration. If you put more reactant particles, there's just more opportunities for them to collide. You put more and more and more, they just increase the likelihood they're going to collide. You increase the frequency they're going to collide. So let's just say more opportunities for collisions. I think I found a silly video online that was talking about dating and reaction rates, and it was silly, but there was some animation, and the silliness sometimes makes it memorable. The other thing we can do, and you kind of have a sense of this, if you increase the temperature, reaction rates really go up quickly. Well, we know temperature is, roughly speaking, a measure of the speed of the particles. So if the particles are moving around slowly, they hit each other once in a while. If you get them moving faster, they're hitting each other, slamming into each other more often. So we could say more frequent collisions They're just rolling the dice more often. They're just bam, 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 flying around, hitting each other. More frequent collisions. There's just more chances that they might get a reaction to happen. The other thing is each collision is a higher energy. If the particles are moving faster, they have more energy. So there's more likelihood, the odds are greater, that when they hit, they'll have enough energy to make the reaction happen. So we'll say higher energy collisions. And lastly, this idea of a catalyst. Catalysts work in a lot of different ways, and frankly, some we don't know how they work. We just know that they do. But one way to think about it is, if I want reactants to interact with the right parts aligned, if I have a catalyst that somehow holds one of the reactants or both of the reactants, or some catalyst might take a reactant and sort of tweak it in a way, stress it in a way that the bonds that need to break are already stressed and it's sort of ready for the other reactant to come in there. In biology, you call them enzymes. These giant molecules, and they have like a little spot, a little perfect spot for one reactant to fit into, and sometimes in another spot for another reactant to fit into, or one just sort of holds it in place. The enzyme holds it in place while the other reactant comes in, hits, and boom, you get a reactant. So I'm going to say catalyst, enzyme, and it just somehow facilitates, typically orientation, I'm going to say. Let's say facilitates orientation. There's a catalytic converter in your car, and basically it forces the pollutant molecules to stop or slow down, and they skitter around on the surface of that catalytic converter. When they're skittering around on the surface, it's easier for them to be lined up when they do collide. And then we said, okay, the last big idea in this chapter was equilibrium. And what we notice hello, that's easy for me to say. At equilibrium, the concentrations are unchanging. So we'll say they do not change. We've got a certain concentration of reactants, certain concentration of products, and that's it. The reaction just doesn't go any further as long as I don't change the temperature. So what's sort of confusing is that we sometimes think, oh, the reaction has stopped. The reaction hasn't stopped. The reactions are, there's a forward reaction and a reverse reaction. They're still happening, and the rates are equal. They're just opposite sign. If something's making 10 moles per minute forward and something else is making 10 moles per minute backwards, you go, oh, they're still reacting, just the rates are equal, so there's no net change. Now, let's see, we didn't really get into this semester. Delta G at equilibrium. At equilibrium, there's no tendency to do anything. There's still reactions happening, but there's no tendency to sort of make more products or go back to reactants. The funny thing about delta G at equilibrium, it equals 0. That is so cool. All right. Well, how far do we measure how far our reactions go? There's our K equilibrium. And remember, it's a ratio of products to reactants. The more products it makes, the less reactants there are, the bigger the number. If it doesn't make much products, the product's small, reactants are large, the number is the overall number is small. Products over reactants, so I'd say F minus, remember that means the concentration of fluoride times the concentration H3O plus. That's moles per liter, moles per liter. On the bottom, HF. And I don't use that, right? I think it was just 1. Mathematically, think of it as 1. Products over reactants ratio, basically. Okay, now, this sort of brings up this issue. We talked about how fast a reaction is going, and we talked about whether it's favorable wants to go or it favors products. So the speed and the delta G or the K equilibrium are completely unrelated. What it means is we talk about it in 2 different ways. We say, well, does this make a lot of products or not? Is this very favorable? Is delta G a big negative number or not? That tells us whether or not the reaction will happen. In between is that speed bump. They're completely independent. There was an example in the lecture or homework or something about rust. Well, rust happens. It's favorable. You put some iron and some water and some iron and water, and it'll rust. Some oxygen, it'll rust. But it doesn't happen very fast. So yes, forming rust is favorable. Negative delta G has a large K, but it isn't fast. So those things are unrelated. And the last thing we did was we said, well, let's not do any math, but let's think about what if you have something at equilibrium and you disrupt it? What if I increase or decrease the amount of reactants? Or I increase or decrease the product's concentrations. And you can do it. You could put more reactant in. You could take reactant out. You could put some product in, remove product. The other thing we said is, well, what if I add or remove heat? Basically, change the temperature. I can usually, well, we'll just say this. What if I change the pressure? So change the concentration of reactants or products, heat it up, cool it off, compress it, expand the container to change the pressure. And Le Chatelier says it will run the forward reaction or the backward reaction to try to bring it back to the same conditions it was before it was disrupted. So I'll say it in Le Chatelier's words. I will try to undo the disruption by increasing the forward reaction or the reverse reaction to get it back to equilibrium. It may not be able to bring it back to the exact number, but the forward reaction will happen or the reverse reaction will happen to sort of undo it as best we can. All right, folks, that's chapter 7. That's huge. And it's maybe one of the more challenging chapters, but it's got the biggest ideas, so that's why we spent 2 weeks on it. All right, thanks for hanging in there. Keep hanging in there. We will get through this mess. See you at the next chapter.